Hi, I'm Krishna. So, in this video, we're talking about optimization. The simple idea that an optimizer is the rule we use to update weights of the neural network. I'll add visuals as we go, so watch for the cues. When backpropagation finishes, it gives us gradients, numbers that say which direction the loss goes up or down if we nudge a weight. But gradients alone don't update anything. We need an optimizer, the strategy that tells us how to use those gradients. We are basically hiking down a mountain of loss. X-axis is weight, y-axis is loss. In real life, we have millions of parameters, so the landscape is insanely high dimensional. But we are smart monkeys. We represent all of that mathematically. The earliest method was full batch gradient descent. Calculate the exact gradient over the entire dataset and then step in that direction. Pros, it's precise, but cons, it's painfully slow and computationally expensive. So we move to SGD because waiting to compute gradient over millions of samples, every update is torture. So SGD, stochastic gradient descent. Instead of using the whole dataset, it updates weights using just a mini batch. The update rule is same as full batch, but the only difference is it uses a mini batch to calculate those gradients. But this gave us huge speed up, ability to train on large datasets, acceptable gradient estimate. But it creates a new problem. SGD is noisy. It jumps around in narrow valleys of loss weight graphs. It zigzags like crazy. So we move to momentum because we needed stability and smoother updates. So momentum, full name stochastic gradient descent with momentum. Momentum remembers the previous update direction and mixes it with the current gradient. Conceptual formula is on the screen. In simple words, V is velocity, a running average of the past gradients. Beta, usually zero point 0.9, controls how much we remember. What momentum does is smooths the path, speeds up movement in the right direction, ignores tiny bumps, and escapes small local minima. Momentum is smoother, but it still uses one global learning rate for all weights, not ideal for sparse data or deep architectures. So, AdaGrade. Remember, we are talking about optimizers, the strategy that we use to update weights of a neural network. So, AdaGrade adapts the learning rate for each individual weight based on how often it is updated. So, here's the intuition. Rarely used weights get big updates, as AdaGrade assumes that this weight has not been explored enough, so it needs a little push, whereas frequently used weight get tiny updates. It is perfect for sparse data like text. Think bag of words, but think about it. AdaGrade's learning rate shrink too much over time. Eventually, updates become tiny and training stalls. To fix this, we have RMS prop, root mean squared propagation. As AdaGrade keeps accumulating squared gradients forever, which makes the learning rate shrink to near zero. RMS prop solves this by using an exponential moving average of squared gradients. So old information fades instead of piling up. RMS prop prevents learning rates from collapsing faster than AdaGrade, works well for RNNs and noisy gradients. RMS prop improves AdaGrade but still lacks proper momentum and bias correction, which leads directly to ADAM, the state of the art optimizer used today. ADAM is adaptive moment estimation. It's the king, the default, the optimizer behind almost every modern model. ADAM is RMS prop plus momentum. It keeps track of M, moving average of gradients, momentum, and V, moving average of squared gradients, RMS scaling. Benefits: fast, stables, handles sparse gradients, handles massive models, works even with messy loss landscapes, converges well with minimal tuning. Adam just works across almost every architecture. But still we have AdamW. AdamW is Adam with correct weight decay. This is what GPT-3, 4, 5 and most transformer models use during training. Adam built-in regularization was flawed. AdamW fixed weight decay and made training more stable. So you might be wondering which optimizer is the best. Short answer, none. It depends on your use case. AdamW best default for most deep models, LLMs, transformers. AdamGrad for sparse problems. And full batch GD is mostly academic. Most practitioners start with AdamW, tune the learning rate, and then adjust if needed. So that's optimization, a journey from slow, expensive gradient descent to more stable methods like AdamW that train the biggest models in the world today. If you want to read and watch more about each optimizer, I've added links in the description. Go check it out. And see you in the next video for activation functions. The thing that actually makes neural network learn non-linear patterns. Let's do it.